Great, thank you very much. Good morning, everybody. So what I'm going to tell you about today are some exciting developments in parallel architecture, some exciting developments that mean that Erlang is going to help us to be able to use these architectures. And this is work that's been funded over the last 3 years by the European Union. We're very grateful to them for doing that. The project has involved various people, including particularly Erlang Solutions partners from AGH who've been working on Erlang. This is a university in Poland. Also, Elta and Eltasoft from Hungary. They're going to tell you more about some of the work this afternoon. Melinda Toth will tell you about that later on. So first of all, to motivate where we are, today everything is going multi-core. Even this little laptop from which I'm doing the presentation is a multi-core device. How many cores does my laptop have? Audience question. Any guesses? 8? 16? 2. Okay, you guys think I'm rich, right? This little device that's from 2011. Internally, it has 2 x86 cores. But these things, they're hyper-threaded, so maybe there are really 4 in there. But in addition to those 4 possible cores, it also has 12 GPU units. It has a device which is just for power management. It has a Bluetooth controller. It has all kinds of other processors sitting in it. If you count them all up, what you discover is that this little device that I'm using here, just to do my presentation, has approximately 20 or 30 cores in it. And this is something at very small scale. At this point in time, we can only take advantage, probably, of the CPU cores, maybe the GPU cores. But in future, what we're hoping to do is to make full capability of these systems available to you as the Erlang programmer. So today, Intel has stretched this. Last year, they released the Intel Xeon Phi in 2013. This is a Manycore device. It has 60 cores integrated into a single package. But what you'll probably notice is these cores are incredibly slow. And overall, the package uses still 300 watts of power. This thing, okay, it's got a lot of cores, but they're slow cores, and it's still consuming far too much power to go into a little device like this. But this, Intel believe, probably is the future for processor chips. This is today the fastest computer in the world. In a month's time, it might not be because they're going to release a new list. But since 2013, this has been the fastest computer in the world. Does anyone know what it is? Sorry, I can't hear you. I'll tell you. It's the Tian-2 supercomputer at the Chinese National University of Defense Technology. I have no idea what they're doing with that. I'm not sure I want to know. This device has 16,000 nodes. Each of them has 2 Ivy Bridge multicores. So those Ivy Bridge multicores are maybe 16 cores each. And each of the nodes has 3 of those Xeon Phi chips, each of which has 60 cores built into it. If you total it up, what you'll discover is it has 3,120,000 x86 cores. Not these tiny parallel cores that Costas was telling us about yesterday. These are real honest-to-God x86 cores. This is probably the world's first Megacore computer. So what are these future computers going to look like? This is where we're scaling to. Well, I can tell you for a fact that they're probably not going to be shared memory. Okay? Not all memory is going to cost the same to address. Maybe you'll have some way of distributing the memory using hardware. Maybe, if Intel can get it to work, you'll have hardware transactional memory, so you ship stuff off. But the idea that you just go and access memory location and get some data back from it is not going to reflect the hardware reality. All these myths that conventional programmers have built up about cheap and easy access to all the memory at the same time just doesn't happen in a device like that. So assuming a fully shared memory is not going to work, but most of the models that we have today to address this, for example, partition global address spaces, divide the memory area into lots of different spaces, they make the programmer do all the work. Now, as Erlang programmers, you guys know this is a stupid model, right? Shared memory is not the sensible thing, particularly for a large-scale machine. What you want is to have shared nothing. The model that Erlang has is going to be a nice fit to these future machines. In particular, side effects across a system like that will not work efficiently and effectively. This is going to be a big shock to most programmers. It's okay to ask, we know that you don't need side effects. So, where are we going? In the long term, what people want to build, and when I say the long term, I mean 2020, what they want to build are exascale computers which will have a quintillion operations per second, the power of something like 50 million laptops. Okay? It's almost inconceivable how much computing power these devices will have. Or possibly what applications they're going to run, apart from cracking my messages in WhatsApp to my wife, or something like that. But very importantly, what you'll notice over here is that the power consumption of these devices is anticipated to be something like 100 megawatts. So these supercomputers, they will consume enormous amounts of power. You'll need to build almost your own power station just to run one of these devices. This tension between energy and power is permeating all the way through the computing devices that we're using. At this point in time, it's most obvious with these really high-end devices, but ultimately, what we're talking about these days is how much computing performance do you get for each joule of energy that you put in. And various people have mentioned this in the talks before. Costas has mentioned it earlier, for example. So, I think this is Megacool. But now I can't see anything. Or maybe it's really mega hot. Energy usage scales linearly with the number of cores. This is why we're going for multicore. As you add more cores, the energy usage goes up with the number of cores. But if you increase the clock frequency, the energy usage scales with the cube of the clock frequency. There's a little graph over here from a computer science textbook called Patterson and Hennessy on computer architecture, and what it shows is that in roughly 2005, we were the fastest chips, Pentium 4s, internally were producing as much energy as a hot plate, so you could cook eggs if you could get inside the chip. If we had continued to scale them, by 2010 or thereabouts, we would be up to the same heat internally as a nuclear reactor. And by today, we would be sitting around with rocket nozzles on the back of our laptops. Okay? Clearly, that's a problem. And this is the fundamental issue which has caused us to go into the multicore, and then the Manycore, and then ultimately the Megacore world. And we're trying to help you do that. But of course, does it scale? Well, if you're going to go to a Megacore machine, what you're going to need is millions of threads. So here's a little application I knocked up earlier. This application, it's just a test bed. It runs for about 20 seconds of execution. And what you can probably see down here is a number. I won't get too close because I won't be on the microphone, but it says 331 and then something like 5872, etc. This is not my phone number. This is the number of threads that this application creates in 20 seconds of execution. That's a lot. 331 million threads in 20 seconds. The application is running on something like a 16-core machine. So how do we do that? We've got 331 million threads. We're running on a 16-core machine. How do we deal with that? Well, what you've got to do, well, if you're in Java, I'm afraid you're stuck. Java is not going to cope, probably, with 331 million threads. But because we're running Haskell, what we can do is to take our 331 million threads and figure out, well, actually, because we've got a much smaller machine, we only need 20,000 of them to keep the machine occupied. Now, which 20,000 is a pretty hard task. You're certainly not going to go around as a programmer and say, okay, I need that one and that one and that one and that one. This has to be fully automatic. Automation has to be in there as we go to these large scales. So why do I want 331 million threads if I'm only going to run 20,000 of them? Well, the short answer is I want to write an application that could run on a much bigger machine. If I don't write my applications to have the scale today, when these machines come along tomorrow, what I've got will not scale. It will fall over. I will spend a huge amount of effort trying to increase the scalability. It's much better to have sufficient scalability already in your application from the outset, and then to squeeze it down, but not have enough, and to try to get more threads to increase the amount of work later. That never works. Having too much, cutting it down, much more sensible approach. So what I'm going to do is to reprise how to build a wall for you. Some of you may have seen this before, but I think it's a good little example that illustrates the problems of how you parallelize programs. So I gave that presentation, and Ian Watson, who's a professor from the University of Manchester, said to me afterwards, well, that's all very well, Kevin, but not all applications are parallel, right? There are going to be things that aren't parallel. And I'm a computer scientist. I like a challenge. So I said, well, what, Ian? And he said, well, say you're building a wall, right? You put a brick down, you put another brick, and so on. And now you've built a row of bricks. And then you can put the next brick down. And now we've built the second row of bricks. And we do the third row. And now we have a wall of bricks. And that has to be a sequential process, right? Wow. I'm going to try to make it parallel. So let's imagine that we have 4 bricklayers here. These probably have to be Swedish bricklayers rather than British bricklayers, or this won't work. But what we can do, for example, is the bricklayers can each lay a brick, and then we lay another row, another set of bricks. Now we've got the first row, exactly as we had before. And we can do the same on the second row, and we can do the same on the third row. Now we've got a wall. So clearly this is done, we've done this in parallel. We've speeded this up. So great, that's fantastic. How much faster was that? Twice? 3 times? 4 times? More than 4 times? Not getting any audience reaction here. Go on, stand out on a limb. How much faster is that? You're smart. 5 times. I've only got 4 workers here. So theoretically, that's impossible. 4 times. Less than 4. Less than 4. That's safe. You could be more precise. Let's work it out. So 3 bricks. So it can only be 3 times faster at this point. And another 3. Also 3 times faster. Now we've got 3. Now we've got 4. So it's a bit more than 3. And another 3. Okay, so it's still a bit more than 3. And another 3. And a final 3. So it's a bit more than 3, but not quite up to 4. If we use the same algorithm, even if we put 1 million workers onto this problem, it would still only go at the same speed. So to make this go faster, what we'd have to do is to break the problem down. There are fundamental limits on how fast an application can go based on the number of tasks that we have. Okay, so the number of workers is a limit, but is not the only limit. There are limits which are fundamental to the algorithm as well. And that's the important point. We have to find the algorithmic limits as well as some theoretical number of worker limits. So here's how not to build a wall. Brick, 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 and so on, and eventually we get the wall. Okay? Nobody's laughing. It's ridiculous, right? Are there any Haskell programmers in the audience? Are you keeping quiet? Well, for the benefit of any Haskell programmers, this version is functionally equivalent to the one that I showed before. It's exactly the same wall. I've just ignored a few little side effects, like gravity. Okay. So the reason this is idiotic is because if we build a wall like this, the bricks higher up, when I do this, are not supported. The fundamental support they need is not available. What matters is that I have the right support for each of the bricks that I'm placing. That is the right data, the right task dependencies for the tasks that I'm constructing. Once I've got that, then I can run later tasks. So can anyone think of a better way to build a wall than the one I showed you on the previous slide? Yeah, each worker can move vertically. Not exactly, because when you can't put the brick, you can put this brick here, once you put that one there, but then this one depends on two others, okay? So it's a little more complex than just going vertically. Once you've got to this stage, you can't place the next one. But having placed that one and that one, you can place two, and then you can place these ones, and so on. There's an ordering. Perfect. You have to identify the ordering. So that's one way to do it. What people sometimes say when I give this presentation is, well, you're being a complete idiot. What you do is you pre-assemble each of the rows, and then just bring them in. But then, of course, you're ignoring the dependencies. So you have to fix up the dependencies when you put the wall together. Okay? So you can do that if you're very, very smart. But what you have to do then is to basically leave a hole where your dependencies are and fill that hole in later. And in a lazy language like Haskell, it may not be too hard to do that. In a strict language like Erlang, it can be a problem because you don't have the data to fill the hole. Good. So how not to build a wall? So we need structure. So task identification is not the only problem. You also need to consider lots of other issues. Coordination, who does what. You need to consider communication, because if these bricklayers are not communicating with each other, they're going to trap their fingers, etc. You need to consider placement, which of the workers deals with which brick. You need to consider the scheduling, the precise order in which the bricks are placed, all kinds of complex issues. Now, if you're doing this using a typical concurrency approach, then the programmer has to deal with all of these issues. And that can limit the scalability. It also takes a lot of time and is potentially a huge source of coding errors. What we want is to have structure and abstraction and not just another brick in the wall. So what I'm trying to do is to teach people how to think in parallel. And this is a slightly different mindset. You may think that thinking concurrently is enough, but it's not quite enough, I'm afraid. You have to start to think not just about the dependencies, you have to start thinking about breaking the dependencies. Thinking outside the box, what is necessary and what is not necessary in your code. So in particular, you might need to deal with hundreds of millions of threads. If I'm writing a concurrent application, typically what I will have will be 10 or 20 or 30 very similar threads. In a parallel program of the kind that I've described, I've got hundreds of millions of them. I cannot possibly know and control what each of those threads is doing. It's like having a hive of bees. You can't know each bee in the hive individually. A few of them you might. Whereas concurrent applications typically are like getting your children or your colleagues to work on something. You can know what each of them is doing, and if there are only 5 or 10 of them, well, that's a lot of children, but if there are only 5 or 10 of them, you can probably keep a track of what they're actually doing. But much more than that, it's impossible. You need to have models that don't allow you to introduce deadlocks. Okay? So as soon as you're in a situation where you could introduce deadlocks and you have millions of threads kicking around, you're going to spend your life debugging these weird deadlocks. And sure, it's great to have tools that can analyze your program and detect the deadlocks, but it's a bit like having a very good cancer doctor who will cure cancer for you. It's great to do that, but personally, I'd rather not have it in the first place. It's much better not to have the disease than to have a really good cure for it, because the cure is never 100%, and it takes time, and it's painful. And you can't program effectively whilst you're fiddling around with communication, worrying about how each of these million threads is going to interact with the others. It's far too low-level a design. You will never be able to understand the interactions between millions of threads. It's literally impossible to do that. That way lies insanity. So the approach we're taking in Paraphrase, the party approach, is to start bottom-up from your program, which could be an existing one or a new program. Doesn't really matter. If you're starting from an existing program, you might have to go through some additional steps. Identify bricks in your program, components, and we use a semi-automated refactoring tool using Wrangler and or Refactel to help us identify the components of the program. So we're using well-known existing technology to do that. Think about the pattern of parallelism. So what kind of pattern do you have? What structures do you have in the problem? So we've spoken a lot about patterns. I'll reiterate that in just a second for those who've not seen any previous talks. These could be things like map, reduce, task farms, a parallel search where you're looking across a lot of different things to try to find the one or two things that are interesting. That's a pattern that we might have in our program. If you're a mathematician, maybe you've got something called a completion algorithm. What you're doing is just trying to work out all the values that correspond to some qualifier. So find all the values that comply with some restriction and collect them. And you can do that in parallel, but there are very complex dependencies between the things you've found so far and new things that you might create, and so on and so forth. And then structure the components into a parallel program. So turn them into concrete skeleton code, also using refactoring. And of course, then you're going to have to go through the process a few times until you've got a good parallel program. So here's the general approach. Start with the original Erlang source code, apply program shaping to extract to put the program into the right form so it can be patternized. And then if you're an expert, you can just put that through the refactoring tool, which will introduce the patterns for you. But if you're a novice, a beginner, or a professor, and you don't know what you're doing, or you'd like some help, then we've got a very clever pattern discovery tool that Melinda will tell you about this afternoon, which will basically look through the program, kind of Google it, find what patterns there might be, and say to you, this is the best one. Perhaps we think this was the best one. Why don't you try that and see how it works out? Put it through the refactoring tool, and out pops parallel code without any with only the necessary dependencies, without any deadlock, with all the communication abstracted away for you so you don't have to worry about it. Great. So common patterns that we're going to discuss include things like a farm, where you've got lots of workers doing the same thing on different inputs, or a pipeline where you do one thing after the other. People are familiar with this from computer architecture. This is kind of like a function composition. So it's very easy to turn a function composition into a pipeline. And if the arguments are independent, you can then run these things in parallel. So that's a nice pattern, particularly at the top level of a program. Or a map, a data parallel operation, where you apply an operation across all the elements of a data structure at the same time. Okay? So very easy to get a lot of parallelism that way, but of course then the problem is the parallelism is often too small to be used effectively. So you have to worry about how do you group things together to make that work. So the bricks, these are functional. These are functions. What I call a brick is just an expression that we can evaluate in parallel. I've done this in sudo Haskell, sudo Erlang, so please bear with me. What we can now do, having got a brick, is to write in parallel. So if you've got a construct in the language called par, what this will let us do is just say, okay, spark that off. It's a bit like spawning off the brick in parallel with doing the rest of the computation, where the result of the brick is going to be plugged back in to the pattern as we need to. And if you've got a language like Erlang or Scala, this is in Haskell. If you've got a language like Erlang or Scala, what you can do is just pass in a parameter to trigger the computation, because otherwise the computation will happen instantly. You don't want to do that. You want it to happen. You want to create a future that you can then trigger when you need to as part of the execution. Higher order functions can be used to capture parallel patterns. So what we can say, for example, is that we're going to evaluate the function f in parallel with applying the function to the rest of the list. And this will then basically apply the operation that we want, as I said, in parallel across all the elements of a list structure. So you can write that just as a simple higher order function in something like Haskell or in Erlang. And then to build the bricks, all we have to do is just apply the operation that makes the brick to some input. And bingo, what we've got is a parallel implementation of our program. Very, very simple, very, very straightforward. And this idea is the idea of a skeleton. So we've implemented a library like this for Erlang. It's called Scale. Chris Brown did this. He told us a bit about this. He gave us a tutorial on this on Wednesday. So these include maps, farms, reduce, pipelines, also feedback, which I'll come back to in a bit in the talk. When you create a skeleton, what you have to do is construct an abstraction of the skeleton and then instantiate it using an Erlang operation, scale_do. And what this will do is to take your skeleton abstraction and your bricks and basically construct the task structure, the process tree that corresponds to the skeleton you've decided on, plus all the bricks put in the right place. So it will automatically do that for you. Very, very neat. It's fully nestable, so you can have skeletons within skeletons to whatever depth you like. Okay, so you're not just restricted to having a pipeline or a farm. You can have a farm with pipelines inside it and so on and so forth. Very flexible mechanism. So the way this works is you've got a skeleton description, you've got some input items, you apply the scale_do operation to the skeleton abstraction and the inputs, and that goes away, produces the process tree for you, distributes it, and then collects the output, like so. So for a pipeline, what we might have is a name. We use the atom pipe. We pass in a number of skeleton structures, scale 1, scale 2, however many you like. What it's going to do is create a pipeline linking all these sub-skeletons together, pass in the inputs that we've got, apply scale_do to that, puts together a pipeline process tree, and the result of that is going to be the result of applying the pipeline to each of the inputs in turn, where the skeletons, the operations, scale 1, scale 2, these are executed in parallel. Or you can do something similar for a farm. If you've got m instances of the skeleton, what you can do is to apply these in parallel to some input set of tasks, and we get out the corresponding outputs from the farm. So this just distributes the inputs according to this structure. Or from a map, it is very, very similar, except that with map, so map looks a bit like a farm, except with this decomp and recomp phase. What that's doing is splitting the list or other data structure down into smaller structures that it sends off to each of the tasks in parallel. So you don't get this problem of overloading too small granularity with the tasks. So you can split and recombine your input and output. Great. So, little example, ant colony optimization. What an ant colony optimization does is to try to find a good solution to a particular scheduling problem, and so there are n factorial possible schedules for n jobs, and solving this is NP hard, which is computer science speak for, my God, that's difficult, or words to that effect. When I see something like this, I leave it to my colleagues who know better than I do how to deal with it. It's a complex problem. The basic idea that we're doing is that we're going to model a number of ants moving through some set of tracks, and the ants basically are going to go down different paths in the anthill. As they go down, they lay pheromone trails. As we discover good solutions, what we do is we mark that trail with the ant marks the trail with the pheromone. The more ants that go down a particular trail, the stronger the track, and eventually we find the best solution, we hope. So it's basically some sort of heuristic search process that we're doing with this example. Not a classic Erlang example, but what I'm trying to say to you is there are things you can now do in Erlang that you might not have thought of doing. Okay? So we can do some really interesting stuff. So ants can be parallelized using a parallel map. That's pretty obvious. We've got some input coming in. What we can do is distribute the ants across the data that's coming in. So here's our ant colony. And having done that, what we need to do is to pick the best of them. This is basically to work out the strongest trail. We do some sort of update process, and we feed that back in for the next stage. Okay, so this is a rather more complicated structure than we've seen so far. The code for that in Erlang, using our scale library, looks like this. The interesting bit is the red stuff here, where we're creating a pipeline. And what the pipeline is doing is basically this bit here of the task, and picking the best and updating it. And then a feedback. And what the feedback is doing is iterating over the pipeline structure. So the feedback is basically doing that part. So with a couple of relatively simple structures, what we've been able to do is to describe this really rather complicated parallel algorithm and hopefully get a good implementation for it. And then we pass that into scale-do with the inputs, and off it goes, and the ant colony just does its stuff, spits out answers to us. So that's one example. What I'm going to do now is show you a second example, very, very similar, slightly more complicated. Also a meta-heuristic approach for optimization. This has been done by our colleagues at AGH in Poland. They're experts on search strategies. And what they're doing is to use a similar approach to the one I've described, except that we have a number of agents, each of which is located on some evolutionary island, where the islands, as with Darwinian evolution with Darwin's finches, they're disconnected from each other, but there's some way of perhaps them exchanging information. So the agents can do things like die, reproduce, migrate, fight, etc. in some order. And what we're trying to do is to use this to basically find the best solution to some heuristic problem. So basic structure, you don't need to know the detail of this. Some sort of tagging process. We might want to migrate some of the agents between islands, then group them. The agents then do their stuff. We apply some shuffling operation to that, and we just go round the process again. So you see this is very similar in structure to the ant colony. How do we do with that? Well, the first stage is to discover some patterns. And what we might discover is, well, these agents over here, we've got quite a few of them. Let's just farm them. So pattern discovery might say, that's a good thing to do. Now, unfortunately, these three things at the top, it's not easy to do those at once. There may be dependencies between them. So what we might then have to do is some sort of program shaping where we're simplifying the code structure at the top level to put it into the right shape for the parallelization. And having done that, what we can then do is to refactor again, and now we can put in a pipeline between here, here, and here, between the initial phase, the agents phase, the shuffle phase, link it all together with a feedback skeleton. And that involves some manual refactoring. Unfortunately, the pattern discovery tool can't discover patterns that are as complex as this yet. So you'll have to do this by hand. So we've ended up with a much more complex pattern structure. So we've implemented this at AGH in Erlang. We've got 4 different implementations, a sequential one where we started, a concurrent one, which is the obvious way to do things using Erlang. But then we've applied Scale, just to show how the Scale approach works, so with this feedback, etc., pattern discovery, etc. And finally, we did a bit of manual work on the Scale version to tune it a bit. And we introduced some of the sequential parts to deal with the islands, because we found from running the program that was a good thing to do. Here's how this looks in terms of speed up. What you can see is the concurrent application here. This is a low ratio computation communication. What's happening here is that the concurrent one is topping out fairly quickly. There's not much scalability on that. A lot of data being shared. If we just use Scale, we get much better scalability. It's scaling up to 40 or so. That's on a 64-core machine. And if you then do some hybridization, you can get a much even better scaling figure. We're getting a performance of about a factor of 60 on 64 cores, which is pretty good. That's clearly going to keep going up to quite a high level. So we thought this was a good result. But that's not the entire story. Here's some figures that tell you how much time this took to implement. So the sequential code, it's 85 lines of code. It took about 10 days of coding effort to get that right in Erlang by experts. The concurrent code, 353 lines in total, I think it's including the 85, took a further 7 days just to do that work, just to make this version concurrent, to fix all the bugs, etc. Using Scale, in contrast, we've added 100 lines of code, so it's simpler than the concurrent version because we've got the library code sitting around there to do the complex stuff. And that only took a day of effort. And the hybrid Scale version took another 2 days of effort to tune it. So by using Scale, not only do you get more efficient code, more scalable code, but you also get the code much faster. It takes less effort to do that. It's being used within Campania. It's being used within an AdWord planner, so it's being used to sell adverts to us on, and this is available through the Google Play Store. So you can get this. You can run your ad campaigns using our software, using the evolutionary algorithm that I just showed to you. So it's a real example. It's commercial, semi-commercial. Very pleased with that. So just to conclude, we've successfully parallelized applications from a lot of different areas, not just the ones I've shown you, but several other places too, including classical algorithms, classical high-performance algorithms. Programmer productivity has been significantly increased by the availability of both existing patterns and new generic ones, domain-specific ones. The speed-ups we're getting, they're close in some cases to the theoretical value. The automated system produces performance results that are practically as good as an expert parallel programmer, and with almost no effort. That's a nice result. If you have the automated pattern discovery, then it can indeed discover some useful patterns. So it can really help you. So you don't have to sort of scratch your head, poke around in the code, and try to think, where's the best place to put the patterns? Used in production code, and what Chris showed yesterday, the Lapido framework, also lets us to map some of these things onto GPUs as well as CPUs. So we can now accelerate parts of our Erlang code, provided they fit the GPU framework. We can get real performance boosts there at sensible energy usage. So we're pleased with that. Okay, now it's not just about big systems, of course. The same principles hold for small systems. Even mobile phones are becoming multi-core, so don't think this is just about big systems. These techniques apply equally well to small systems. Even mobile phones have GPUs, etc. And if you don't believe me, and you're right to be quite skeptical, because I'm giving you a sales pitch here, right? please go and talk to one of our happy customers, Ramsey from Sheffield University. I don't think Ramsey's in the audience. But what Ramsey said to me, and he's been telling other people, is Scale is great, it's fantastic. All I had to do was just pop it in. My program went much faster, and I was able to exploit some high-performance computing resources that were available to me. And it would have been a lot of work if I had to do it by hand. So please go and chat to Ramsey to get a further endorsement. Lots of industry interested in this. This is my new project. So we've got IBM interested in exploiting these ideas. This project is just starting, and various other companies. I'll leave that up for a second. So this is gaining commercial interest. Thank you very much. Full contact details.
We have time for some questions.
I looked at your code. It wasn't beautiful.
Well, so to answer that, one is it doesn't have to be. Because it's automatically generated. Are you complaining about our library code or the code that's been inserted? Oh, well, the example we've just inserted, we've done this basically for illustrative purposes to show you what's going on. You could obviously have cleaner code there. So yes, we could improve the code that's being written. We can make it tidier if we wanted to. It's certainly possible to have better refactoring tools. We're researchers, right? So we just want to get the job done. And that was quick and easy, quick and dirty. Yeah, you can certainly tidy it up. You can have libraries, you can have abstractions, but we wanted to make everything visible. I think one of the important things about what we're doing is we don't have anything up our sleeve, right? And you can just go in, you can see the code, you can see exactly what's going on. But yes, if you have any ideas for improving the code quality, please tell Chris. He'll be very happy to see that.
Have you done any kind of tests on how many parallel tasks you can run and see if you can do thousands or hundreds or 20, 10, 20 or something like that?
Yes, the question is about scalability. So the highest we've currently got with Erlang is about the 64 here. So we're quite pleased with getting 64 scalability there. I didn't say, we've also done the same thing in C++, and we've used slightly different, we've used the distribution mechanism MPI in C++. We've run the code on 1,500 cores on a 33,000 core machine, and we're getting good linear scalability on that. Okay, so the nice thing about the pattern approach is because it's decomposing, then things will scale. So because you've broken the dependencies, you can have much more parallelism. So in the C code, yes. In the Erlang code, we haven't yet, but there's no technical reason why we can't. Okay, so it's just a matter of practicality. We need to do it. Good question. I hope to see Erlang code running on a Megacore machine sometime very soon. Someone just has to give me access to it.
I have a question also. Does the tool give you any hints on when to use this? Because I guess there's a lot of overhead to actually have a process and send a message than just doing a quick loop in line.
So you're saying, well, what you need to do is you need to feed in performance information. So the party tool, the pattern discovery tool, indeed will say to you, yes, this is worth doing. What it will do is to profile parts of the code. It will try to work out it's got a cost model that tells you about the costs of execution under the different models. And what it will say is, well, I think if you choose this particular pattern at this point, then the performance is going to be the following. It's sometimes wrong because it's academic, right? It's theoretical. But it's a predictor, and it helps. So yes, you can do that. I would certainly recommend using the party refactoring tool, the pattern discovery tool. It's a very cool piece of technology. But you could always measure things by hand if you wanted to. it makes no point to parallelize something which is tiny most of the time.
Any more questions?
I've got one question regarding the dynamic scalability. So, am I correct that basically your pattern recognition allows you to basically suggest some multiple, different patterns to improve the performance of your program? But what about, dynamically adding more nodes or descaling your application at some point? So, did you consider doing something similar to that? So, for instance, not just running on the multi-core machine that has some specific configured number of cores, but basically running something in cloud that you can insert more cores when you need it, and like to scale the number of processes when you don't need them.
Right, so the question is, can we basically scale the system dynamically to include more cores in the system? So you're running low on effort, and you just add another node in. You go down to your hardware shop, and you pull out another server, right, and plop it into the system. So we haven't at this stage done that, because we haven't got the distributed system in there. We've done something similar in other settings. The complication is usually not adding in stuff. It's what happens when you decide to throw it away. Okay, so what you've then got to do is to basically say, okay, I've got these running computations on 2 different machines, and now what I have to do is to grab them off this machine, migrate them back onto one server, and then keep going. And that can be quite slow. The nice thing with the approach we have is that because the tasks are decomposed like this, because we have the bricks, you can essentially smooth the bricks back. And providing the code structure stays the same, you can just keep executing. Okay? So we haven't done it, but that's definitely possible with the model that we've described. The model we've described is very flexible.
Okay, thank you, Kevin.
Thank you.